We are excited to share our paper titled Rotation-Constrained Cross-View Feature Fusion for Multi-View Appearance-Based Gaze Estimation. To start, let me briefly introduce gaze estimation. Gaze estimation is a technology used to predict the direction of an individual's gaze. Typically, this direction is represented by a three-dimensional vector, as displayed in this video. Lately, estimating accurate gaze from a single RGB image has become possible, eradicating the need for any specialized equipment or portable eye-tracking devices. Potential applications of gaze estimation could range from scrutinizing public display interactions to analyzing a driver's focus. Nevertheless, from a machine learning standpoint, accommodating the extensive diversity of human faces poses a challenge. For instance, factors like significantly varying lighting conditions or unconventional head poses could complicate and impact the accuracy of estimation, as you can see in these bottom examples. Adding to this, gaze estimation datasets are challenging due to the high costs associated with annotation. It's worth noting that annotating post-capture isn't feasible. Therefore, it's crucial for gaze estimation models to possess a domain generalization ability. The ideal scenario is training a single model in the lab that can then infer in any environment without requiring additional training. Our motivation is that, with the recent significant reduction in the camera cost, it becomes feasible to assume scenarios where multiple cameras are readily available. Since multi-view inputs compensate and aggregate the information to a more comprehensive facial understanding, which is expected to be more robust and generalizable to unseen environment. Therefore, we formulate a task named multi-view gaze estimation. The task requires two input images and provides a gaze vector as output. Using two cameras has substantial merits. It expands camera configuration possibilities for improved eye visibility and simplifies capturing the three-dimensional facial features. Second, there may exist physical constraints of the cameras such that we can apply to the face features. Our key idea is to explicitly use the physical constraints between two cameras, specifically their relative position. If we refer the primary image as target and the additional image as reference, which are assumed to be synchronized and calibrated, the camera's relative position can be represented by a rotation matrix R, as formatted here. Since this is done in the normalized space, there's no freedom in translation. We propose directly applying the rotation matrix to simplify the utilization of features from different views. Specifically, we explicitly multiply the rotation matrix to the features to transform features between views. We initially reshape the features into a 3xD form such that the multiplication is posable. Thus, transforming the features to align with other views no longer relies on learning, leaving the MLP's role solely as a feature fusion tool from the two views. Since not all facial properties can inherently rotate, our next focal concept is to split the features to rotatable and non-rotatable features by repeatedly fusion. Rather than instantaneously producing accurate three-dimensional features, we believe it's more effective to rotate the feature and gradually update it, ensuring growing consistency between the two views' features. Moving on, I'll elaborate on our specific network architecture. Firstly, we extract features independently from each image and obtain a feature vector, denoted as a lowercase f. Next, we pass the initially extracted feature vector through an MLP to obtain three feature vectors. By stacking these, we create a D times 3 feature matrix, which is compatible with multiplication with the rotation matrix. We then apply the rotation matrix to each resulting feature matrix. Following that, the rotated feature matrix and the initially extracted features are fed into an MLP to update and acquire a new set of rotatable features. Finally, an MLP is applied to these features to execute separate regression for the gaze direction in both the target and reference images. The aim of repeating this process of feature rotation is to further separate rotatable and non-rotatable features. Now, let's look into our experimental setup and results. We use two datasets, ETH-X-Gaze, which includes 18 synchronized cameras capturing subjects from different angles along with camera parameters, and MPII-NV, a synthetic dataset created using a face model. The latter rotates a 3D face model built from a single front-facing picture to generate data. We format experiments to verify the generalizability for novel head pose. While the scene conditions use same head pose for training and inference, the unseen settings utilize 12 cameras for training and 6 for testing, including interpolation and extrapolation. In terms of the subject splitting, we conduct k-fold within dataset evaluation for both datasets. The subject splitting is shown in this table. We also conduct cross-dataset evaluation using these two datasets. Let's look at the first experiment's results. This table illustrates the accuracy of each baseline and our proposed method. The used metric is the angular error between the estimated gaze direction and the actual direction. Our proposed method significantly outperforms other methods, demonstrating notable robustness, especially regarding novel head poses. Next, I'll share the cross-dataset evaluation results. The first row illustrates the outcome when we trained on XGaze and tested on MPI-NV, while the second row presents the reverse, training on MPI-NV and testing on XGaze. Notably, our approach achieves high accuracy even in a cross-dataset context. We also conducted an ablation study, assessing the accuracy of multiple versions of our proposed method, each incorporating the rotation matrix into the features differently. The method on the left neglects the rotation matrix. The one in the middle flattens the rotation matrix and directly inputs it into the MLP, while the rightmost method is our proposal. Investigation of the left and middle methods confirms the rotation matrix's effectiveness. Still, the highest degree of robustness is achieved by multiplying the features by the rotation matrix. Next, we investigated the activities within the MLP that encodes the rotation matrix and our model. During inference, we calculated the gradient for each image feature to determine how much the target and reference images contribute to the final inference. This table displays the target's contribution rate. Red spots indicate a higher reliance on the target image. When the rotation matrix is merely encoded with an MLP, inference relies predominantly on the target image, regardless of the nature of the incoming image. However, our approach showcases the proper utilization of the reference image. Lastly, to examine how closely aligned the features are, we embedded features from the first block using isomap. In this figure, circles and squares represent the embedded features of the target and reference images, respectively, while arrows signal the transformation caused by application of the rotation matrix. This confirms that applying the rotation matrix directly to features results in a rotation in the feature space as well. In conclusion, we've introduced a new task of gaze estimation using multiple non-fixed camera pairs. Additionally, our approach achieves notable accuracy and robustness in this setting, particularly with novel head poses. Nonetheless, our method is considerably reliant on accurate calibration. Thank you for your attention.